Okay, what if I told you that our entire experience of time, the past, the present, the future, that feeling of it flowing, is really just a form of cosmic friction? That we're not being carried along by time, but we're actively pushing against it every second of our lives. Today we are diving deep into a truly radical new idea. It suggests that time isn't fundamental at all, but something that emerges, something linked directly to mass and the very field that gives everything substance.
So to really get your head around how wild this new theory is, you first have to understand the huge problem it's trying to solve. You see, modern physics kind of has a split personality when it comes to time. On one hand, you've got Einstein's general relativity, where time is a physical dimension woven into space-time, something that gravity can literally bend and stretch. But then you have the quantum world, where time is, well, it's just a background clock, a metronome that ticks away for everyone, everywhere, at the same rate. And the problem is, these two ideas are completely, fundamentally incompatible. It is one of the biggest roadblocks in all of physics.
But what if both of those theories are missing the real picture? A fascinating paper by a researcher named Hamidi Wakid puts a third option on the table, the viscosity model. And it asks us to just completely flip our understanding on its head. It says time isn't a dimension we travel along, and it's not some universal clock we all listen to. No, it's something else entirely.
And this is the core idea, the central analogy. Forget about the river of time that carries you along. Instead, I want you to picture the entire universe being filled with an invisible, incredibly thick fluid. In this picture, the experience we call time is nothing more than the resistance, the effort we feel as we push our way through this cosmic goo. It's not a journey, it's a struggle.
Now, this idea has a name, scalar drag. And that thick fluid I was talking about, that's the Higgs field, the invisible energy field that permeates everywhere, everywhere. It's the very same field that's responsible for giving fundamental particles their mass. So this model says that as particles with mass, like you and me, move through space, we're actually dragging against this field, creating friction. And that friction, that scalar drag, that is what we perceive as the passage of time.
Right, so if time really is a kind of friction, this connection between having mass and experiencing time has some pretty profound consequences. It means the amount of time you experience should be directly tied to how much friction you're creating.
And that leads to this incredibly simple but really powerful fundamental rule. The more mass an object has, the more it interacts with the Higgs field. The more it interacts, the more scalar drag it feels. And therefore, the stronger its experience of time is. So in this model, time isn't universal at all. It's personal. It's tied directly to your own substance.
And this relationship just pops right out when you start to look at different particles. So all the way on the left, you've got a photon, a particle of light. It has zero mass, so it experiences zero scalar drag. Its experience of time is zero. Then in the middle, you have something like a neutrino, which has an unbelievably tiny mass. It feels just a whisper of this friction, right? A tiny little tick of the clock. And then there's us, made of heavy baryonic matter. We are absolutely massive in comparison, so we are constantly pushing against this Higgs field, creating a strong, relentless experience of what we call duration.
And, this is one of the most elegant parts of the whole theory. It provides a simple, mechanical reason for something we already know is true from special relativity. For a photon, time literally doesn't pass. The viscosity model gives us the why. No mass, no friction, no time. It's that simple. It's not a patch, it's a natural consequence of the core idea.
Okay, so if more mass means more time, a stronger experience of time, what happens when we take that idea to its absolute logical extreme? What happens in a place where mass and density become almost infinite? Yeah, let's talk about black holes.
Let's go back to that cosmic fluid analogy for a second. We all know from just our everyday lives what happens when you put a fluid, like water, under extreme conditions, right? Under extreme cold, it freezes solid. But what happens when you put it under extreme pressure?
Well, this model makes a truly startling prediction. The insane gravitational pressure inside a black hole doesn't just squeeze matter, it squeezes the Higgs field itself. And just like water can form all these weird kinds of ice under high pressure, this theory suggests the Higgs fluid undergoes a phase transition. It crystallizes. It turns from a thick fluid into a rigid, solid lattice. The viscosity becomes infinite. And if time is just our movement through that fluid, then at the event horizon of a black hole, time freezes solid.
Now, this is a massive departure from standard physics. I mean, the conventional wisdom is that at super high energies, like in the early universe, the symmetries of physics get restored, and the Higgs field basically turns off. But this model says the extreme pressure of a black hole does the exact opposite. It doesn't restore symmetry, it breaks it in a totally new way, forcing the field to lock into a solid state.
A quote from the original paper really captures this mind-bending idea perfectly. The event horizon, the edge of a black hole, isn't just a point of no return, it is a phase boundary, just like the surface of ice on a lake. The moment you cross it, you enter a region where time is no longer a fluid you move through, but a frozen, static crystal. Information isn't destroyed, it's just locked in place in a timeless, solid state.
So this is an incredible story, right? But is it actually science? Because a cool idea is only as good as its predictions. And the good news is, the viscosity model makes a concrete, testable prediction that could, one day, prove it right or wrong.
And the key isn't to look at really massive things or massless things, but to look at the particle that's somewhere in between. The perfect test subject for this theory is the ghost particle of the cosmos itself, the neutrino. So here's the prediction. Because neutrinos have that tiny little bit of mass, they should experience a tiny little bit of scalar drag. It means that over billions of light years, their internal clocks should tick just a fraction faster than our clocks do. Now, you could never see this clock slip directly, but it would have a subtle side effect. As neutrinos travel from distant galaxies, they should change their flavor, or their type, at a rate that is slightly different from what standard physics predicts. We could actually see this as a weird anomaly in the data we collect.
And this number really gives you a sense of why the neutrino is the perfect key to unlock this. Its interaction with the Higgs field is minuscule. We're talking about a trillionth of that of other particles. This means its friction with time is incredibly weak, almost zero, but not quite. And it's that almost that makes it the perfect magnifying glass for this tiny effect.
And the best part is, this isn't science fiction. We are building the tools to look for this exact thing right now. These next-generation neutrino observatories, like the massive IceCube Gen 2 detector being built at the South Pole, will be sensitive enough to measure these flavor ratios from deep space with incredible precision. If the viscosity model is correct, its signature might be sitting right there, waiting for us in that data.
So, what does this all mean when you boil it down? Well, this model offers a potential bridge, a unification of two of the most fundamental concepts in our universe. It suggests that time and mass aren't really separate things at all. They're intimately linked through one single physical process, friction with the Higgs field. Our experience of duration, it's the price we pay for having mass.
And that just leaves us with one final, lingering thought. For our entire existence, as a species, as a planet, we have been swimming against the current of this cosmic fluid. But this theory suggests that timelessness isn't some fantasy. It's the natural, fundamental state of things that are massless. So it really makes you wonder, if our very sense of being is defined by this temporal friction, what would it even mean for that friction to finally stop?